So thanks very much for having me back, and thanks very much for not asking me to provide you with a background check. Awful. Is there any chance we can turn that?
They will get the.
Perfect. Okay. I'm a theoretical astrophysicist out at UCSB, and I've spent wasted my life trying to understand these disk-like structures that orbit gravitating objects like black holes, like you just saw in the planetarium show. I'm wondering how I'm going to top that, but I will attempt that. So what I thought I would do is this time is give you a broad overview of what these rotating disks are all about, starting from Saturn's rings all the way out to quasars, and then tell you about, actually, I've talked about black holes here before, but frankly, I'm getting bored of black holes. Despite the show that you just saw, I'm not saying that you should be bored of black holes, and I'm actually most excited about white dwarfs these days, so I'm going to show you a little bit about the research that we've been doing here at UCSB on that front. So let me go ahead and get started then. So yes, I told you that I would begin with Saturn's rings because this is the closest example of something sort of like an accretion disk, except it's not actually accreting because there are moons orbiting Saturn that confine these rings into these beautiful structures. That, in fact, a very, very rich structure that Cassini just filled us with tons of details on this. But basically, a disk is simply consists of material. In this case, rocks, pebbles that are in orbit around a gravitating object, where gravity is being balanced basically by the rotation of the material. That had to have happened on a much larger scale here in our solar system. You all know because you're good astronomers, that all the planets travel around the sky on the ecliptic, or near the ecliptic, through the constellations of the zodiac. The exception is this one, but this is not a planet, right? So, to be clear. Oh, come on! Wow, I can't believe this is still controversial. So the things that are bona fide planets in our solar system all travel around the same path on the sky because we're looking out through what was a disk of material out of which these planets formed. And in fact, we can even see those disks today. So these are images taken by the European Very Large Telescope in the infrared. This is polarized light, so basically scattered light. And this is the fabulous image taken in radio, millimeter wave radio, by the Atacama Large Millimeter Array, or ALMA. And this is a young star, and this is a disk which might be forming planets. And in fact, a popular idea for all of these gaps that are forming are the same thing that you saw in the gaps in Saturn's rings, that there are, if you like, moons that are confining the material. And indeed, planets in formation could form gaps in these disks. The thing that bothers me personally about this is that Saturn's orbit in our own solar system would be about here. So you're talking about giant planets that are on scales much, much larger than the scale of the solar system here. And that just, and you're talking about many of them. And that just strikes me as a little challenging. That's my own personal opinion. I'm a magnetohydrodynamics person, and it turns out that there are instabilities in these disks that it can also cause these gap-like structures to form. Yes?
How does our Kuiper belt compare to those outer layers?
How does it compare? So the Kuiper belt basically starts at Neptune and beyond. That Pluto, I would claim, is a Kuiper belt object, and not a planet again. So this is on the scale of the Kuiper. I mean, it is on approximately the same scale as the Kuiper belt. But the Kuiper belt, as far as we know, doesn't. Well, you've all heard of Planet 9, right? I don't know what the current status of that is. Whether that it hasn't been found yet. Whether dynamicists still think it might be out there, I don't know. So, I mean, it could be that there, but this would, again, I'm not gonna get on my expert soapbox and say categorically that these can't be formed by planets, but it just bothers me that there's so many of them here, and in fact, it gets worse or better depending on your point of view. So ALMA's now cranking out these images of protoplanetary disks in spades. So this came out sorry, we're past the new year, so in 2018. And again, you see all sorts of structures in these disks, including very, very narrow rings. And that I don't see how you can create without sort of shepherding planets. This one I find interesting. This is a binary protostellar system. Each of the stars has a protoplanetary disk. So these structures are very, very common around young stars. Some of these stars are actually only 1 million years old, so they're extremely young, and they have these disk-like structures. Yes, go ahead. Yeah.
The third one.
Third one from
the left.
From the left.
On the top level.
Oh, on the top level. This
That
one.
looks like almost like it's a spiral.
And in fact, that is, yeah, it looks like it is a spiral-on pattern, yes. And so that's also forming in some of these, and that's not unique here. It is, that has a sort of spiral structure, and there are other systems, maybe not.
Third one down.
Yeah, this one here has a. So that is also a common feature that you see in these disks.
What
Yes.
sort of distances are they detecting these at?
I believe it's
Within 100 light years, probably?
no, more than that. So I think I just read this afternoon. I think it's more like 400 light years. 400 light years. Yeah. So 100 parsecs or so.
Wow.
Yeah. No. This is the technology that goes into this is amazing to be able to resolve these structures at those distances. Yes. Yes.
Are the dimensions of these protoplanetary disks roughly the same, or the very large ballpark range?
That's another question that I don't have the exact answer to. I think they're roughly on scales of 100 astronomical units or so, but yeah, for each of these systems, I don't. So, in fact, let me confess to you, as I was preparing this talk today at the last minute, and I knowing this image existed, I downloaded it, put it in the talk, and I started to notice some of the properties of these systems, but no, I don't. Yeah, I'm not yet familiar with them as much as I am on the systems that I work on. But yeah, it's pretty amazing. Yeah, and again, these spiral structures are not. You don't just see them here; you see them in other types of accretion disk systems as well. So this is an exciting and exploding area because exoplanets are all the rage in astrophysics these days, and these are definitely the systems in which planets form. I'm just worried about the bandwagon effect that everyone thinks that all of these gaps that are forming are due to planets, and they may not be. Okay, so these are the systems that I'm much more familiar with, and I've given talks here before on that. Cygnus X1 you saw in the movie in the planetarium. This is this blue supergiant star that they were talking about. There are many other black hole X-ray binaries in our galaxy. This is in fact my Cygnus X1. I really is the system that I hate. This is the system that I'm obsessed with, and I'm much more obsessed about. It's because Cygnus X1 doesn't really do what the others do. The others do things that are really interesting, and again, but Cygnus X1 is very bright, so there's a lot of data on it. But again, these systems, the only reason we're seeing the black holes in these systems is because they're ripping material off of their companion stars, and that material, black holes don't radiate light, so the only way to see them, until recently, was to have material accrete onto them. And again, that accretion process is taking place through a rotationally supported disk. So there's material orbiting the black hole where basically its rotation is balancing the force of gravity. Until recently. So that movie is out of date, you know that, right?
Yeah.
So LIGO has detected the mergers of black hole binaries, and indeed the mergers of one merger of double neutron stars. So you know, we are in a completely different era now because now we're seeing the space-time itself, the dynamical space-time as two black holes merge. We're seeing the black holes because all black holes are warped space-time, and we're seeing the warped space-time directly in gravitational waves. So this is completely transforming our field. And now we're moving even out to larger scales. So those are stellar mass black holes of masses of around 10 to 15, well, 6 to 15 solar masses. This is now an image of Centaurus A, so it's an entire galaxy. This is an optical image. There's that dust line that's blocking the optical light from stars near the core of the galaxy. This is an X-ray image. Everything that you're seeing here, with one exception, I forget which one of these dots it is, which is a foreground star. All of those other dots are accreting neutron stars or black holes, stellar mass accreting neutron stars or black holes. Every single one of these are accretion disks around neutron stars and black holes that are radiating in X-rays. These are not, well, they're stars, but they're very exotic stars. And of course, there's the behemoth at the very center of this galaxy, the supermassive black hole, which is, through its accretion process, squirting out jets of material which are ramming into the intergalactic medium, forming shocks. Again, this is X-ray emission that you're seeing here. And that's a process which turns out to be incredibly important in terms of the overall evolution of galaxies. We now know that this black hole feedback actually matters in terms of the architecture of galaxies that are forming. And
Colors in that X-ray wavelength difference?
yes, that's right. So red are the softer X-rays, and blue, then there's green, and then there's blue, and that's moving at to higher photon energies. That's exactly right. Yeah, the colors are not optical colors. They are, if you like, X-ray colors, right? Exactly. So I'm going out now beyond galaxy scales. This is the Perseus Cluster. And you can see lots of galaxies in this cluster. Unfortunately, this one doesn't have any obvious gravitational lenses, but gravitational lenses of background galaxies, distorted images of background galaxies is a common thing that you see in clusters. I don't see any in this particular image. But this is the central galaxy in this cluster, and you can already see in this optical image that there's some evidence for distortions. And if I zoom in on that galaxy with this beautiful composite, and maybe you've all seen this. So this is a radio, X-ray, and optical composite. So the optical light is sort of obvious. It's basically Hubble Space Telescope colors. But the blue that you're seeing here is X-rays, and this pink is diffuse radio emission. And that radio emission is, again, coming from the very center of the galaxy, and this material is coming out, ramming into the intergalactic medium, which is hot gas radiating in X-rays, and it's basically pushing the X-ray emitting gas away, okay? And again, this is an example of feedback, but now on galaxy cluster scales. In fact, I'm going to show you yet another image of this. So let me go back one. So that was just on this scale here, okay? And look at that companion galaxy there. You can see that here, over there in the X-ray image, this composite image to give you a sense of scale. But now I'm going to zoom out even further and show you the whole X-ray structure, just the X-rays. Okay, so again, just to again orient you, there's the central radio-filled bubble. So this is a bubble in the X-ray emission, and that's that bubble here in the X-rays. And now we're going to much fainter levels to see the X-ray structures. And what you can see is that there's a whole series of bubbles that have been formed over time at different orientations from the central black hole that's been pushing material out, depending on what the black hole and its accretion disk are doing at that particular time. And this galaxy clusters are amazing. Galaxy clusters, for those of you who don't know, should not be called galaxy clusters, by the way. So they're dominated by dark matter, of course, because everything in the universe on these scales is dominated by dark matter. But even in the ordinary matter that makes up stars, planets, people, their mass is not dominated by galaxies. It's dominated by this hot X-ray emitting gas. the mass in atoms and ions mostly because this is so hot, so millions of degrees here, the mass in that gas beats the mass in all the galaxies in that cluster.
Jeez.
Okay, so galaxy clusters are mostly blobs of very, very hot X-ray emitting gas with a few galaxies thrown in for good measure. And it's really because as material falls into these galaxy clusters, it gets shock heated to enormous temperatures, and before it actually forms galaxies. Anyway, it's been a long-standing problem in astronomy as to why this X-ray emitting gas doesn't all collapse in on itself, because you see the X-rays, okay, and that means that this gas is cooling by radiating these photons at us, and as it cools, it loses its heat, and so its pressure support against its own gravity. Remember, this gas dominates the gravitational field. Sorry, it doesn't dominate the gravitational field. Dark matter always dominates the gravitational field. But it's supporting itself against the gravitational field of the dark matter and itself by pressure here. You're radiating away that pressure, and so it should collapse, and it should form what we call a cooling flow. You don't see these cooling flows. So something must be re-energizing this gas, and that something is probably the feedback from the central black hole here. Okay, and we see this on all scales. We see it on galactic scales and galaxy cluster scales. And so again, the overall evolution of these galactic and supergalactic structures is affected enormously by these black holes. So the question is, how do black holes do that, or how do these accretion disks do it? Okay, so forgive me, this is a slide that I think I first created for this club many years ago for the very first talk. So I'm going to show it to you again to remind you, for those of you who were here then. You may recognize it. Here's a cartoon of an accretion disk orbiting this black hole. And the thing that I want to emphasize, the thing that I want to emphasize is that this is a differentially rotating shear flow. So just as Mercury goes around the sun once every 88 days, is it? And the Earth goes around the sun once every 365 days, that's a number that I'm pretty confident about, 365.25, right, days. Things that are orbiting close to the central mass go around much faster than things that are further away. Okay, so in this disk, this material is whipping around near the black hole much, much faster than further out. So it's a shear flow. And if there's some friction in this shear flow, then this material that's orbiting really, really fast is going to try and pull on this slowly rotating material and try and speed it up. And similarly, of course, it's to every action there's an equal and opposite reaction. This slowly rotating material is going to try and torque down the rapidly rotating inner material. That rapidly rotating inner material is therefore going to lose rotational support, and it's going to fall inward, and this material will pick up rotational support and spread outward. But that material that's falling inward is eventually going to reach what we call, and this is an effect purely of general relativity, of Einstein's theory, an innermost orbit beyond which you can't orbit stably. There are just no circular orbits that the material can occupy. It's a purely general relativistic effect. And when it reaches there, it's just going to fall into the black hole. So, as you process material through this disk, as it spirals inward slowly under these friction forces, and eventually plunges into the black hole, bringing it in from infinity or far out down to here, you end up releasing an equivalent of 4% to 42% of its rest mass energy. And that is a huge amount of energy. Nuclear fusion reactions and our hydrogen bombs and our, hopefully one day fusion, I don't know what you believe about it, if that's possible. I won't get into that, but fusion reactions release about 0.7 to 0.9% at most. And this is 4 to 42%. So gravity power by black holes actually releases far more energy than nuclear fusion reactions, which power stars and galaxies. And that's why supermassive black holes can actually outshine their entire host galaxy, because that gravity power is just so much more efficient at processing the equivalent of matter into energy. And that's why they can affect the entire evolution of galaxies. Okay, so now, yes?
That massive power ultimately is all from friction?
it's BS, right? So what is the source of friction? That's complete garbage. So what I just said was a complete lie. Yes. So at least I'm owning up to it, right? Yeah. So so by friction, you might think of this as a sort of viscosity in the fluid, okay? But it can't be that. So real microscopic viscosities are just completely irrelevant in these sorts of flows. The only place that I know of where real viscosity, in some sense, is relevant is Saturn's rings, where the molecules in the fluid, if you like, are the individual rocks and pebbles which actually physically collide and they exchange momentum and angular momentum within those rings, and that's what causes the dynamics. We want the rings to spread out, as I was describing, but then you have shepherding moons that keep them confined. This cannot be due to anything like a viscosity. It's got to be something else. And that's something which is why I'm a masochist in studying this subject for so long, is turbulence. And it's not just fluid turbulence, it happens to be electrically conducting magnetized fluid turbulence. And it's a very, very difficult problem to study, except we're making progress on it. And that's what I'm going to get to. So I want to explain to you where this turbulence comes from. This turns out to be a completely unstable situation, these disks. They're vulnerable to a dynamical instability, and it's an instability that's sort of interesting, even though it has to do with magnetic fields and conducting plasmas, so very complicated physics. You can explain it with a very simple mechanical analogy, which is actually a mathematical, there's an exact mathematical map from the equations of plasma physics that we work with to this little model, and I think it's something that you can all understand. So, imagine you're on a space shuttle, and you're going around the Earth here. Okay, and imagine that for some reason the space shuttle just gets a little push outwards in radius for a little bit, just a little bit. Then does the space shuttle go flying off into space or crash into the Earth because of that little perturbation? No, because its orbit is completely stable. All you do is you change its circuit orbit into a slightly elliptical orbit, and that's it, it's perfectly fine. So let me make the problem a little bit more complicated. Rather than just a single object orbiting the Earth, let's consider two objects, and let's connect them by a spring. So if you like, imagine you're an astronaut, and you're tethered to the space shuttle now. And I'm going to perturb you, the astronaut, inward, and the space shuttle a little bit outward, so the tether starts to get stretched. Okay? The reason why you have that tether is because you want that tether to pull you back toward the space shuttle. You don't want to leave the space shuttle, okay? So, and that should happen, right? Because I've represented this tether as a spring. If I perturb this mass inward and this one outward, the spring will stretch and it will pull you back. You hope. But there's something else that might happen. Fortunately, it doesn't happen to our astronauts, but so the astronaut who got perturbed inward, because the analogy is a figure skater who's spinning. If that figure skater pulls in his or her arms, then you spin faster, okay? And that's due to angular momentum conservation. Whoa. I was already getting a sort of a headache watching the spinning movie in the planetarium. Yeah, I'm getting old as we all are. Okay, so I perturb this mass inwards essentially because of angular momentum conservation. This mass ends up going into a faster orbit around the Earth. Okay, so you start moving forward, and the space shuttle that you're leaving is going into a slower orbit, and so it starts going backward relative to you. And so that drives the spring to stretch even further, which of course will try and pull you back. But the other thing that it's doing is it's also extracting angular momentum from me, okay, pulling me back, which means I'm going to want to drift. I'm losing rotational support against gravity, so I'm going to want to fall in further. And this is gaining rotational support against gravity, so it's going to push outward. So there's another effect which is actually pushing us apart. And the question is, which one of these effects wins? And it's a very simple criterion, it turns out. So this is how it's going to happen further. if the time scale for the spring to pull you back by tension is shorter than the time it takes to go around in an orbit, then you are safe. And that is the case of all tethers that astronauts tether themselves to the space shuttle, so they're perfectly safe. But if this is a very weak spring, and this is what makes this so bizarre, and the weaker the better, so that time scale is very, very long, then if that time scale exceeds the time that it takes to go all the way around the Earth, then this effect dominates, that you're torquing down that inner mass and torquing up this outer mass, and they fly apart. And it's an instability, it's a genuine instability. So if you want to tether yourself to the space shuttle, make sure it's a strong enough tether. Okay? A weak tether, a very weak tether will actually pull you. You'll fly away from the space shuttle. Yes?
What kind of G's, again, would the astronaut be experiencing worse than any dive bomber pilot, right?
I don't think so, because well, not in this case that they're flying apart, you mean?
Well, and the individual inside this capsule would be, his feet are on one end of the spring and his head is at the other, he's in trouble.
Oh, well, but then fortunately our body forces are strong enough to hold me together. If I try and pull myself apart, I will snap back on a time scale much shorter than it takes the hours to go around the Earth. So
it's not, I mean, the way they described it in that film, it's
Yeah.
like a person on the rack in medieval times.
that's right. So right. So there, it's the direct gravitational field of a black hole, and if you're talking about a stellar mass black hole, yeah, the difference in gravitational force between your feet and your head can be gigantic as you approach the event horizon, and so your feet just get ripped off.
That would be the end of you right there.
That would, yes, that would be the end of it, yeah. Okay, so yes, also don't venture near a black hole. That's the biggest advice that I would have. So anyway, when you do so magnetic fields and disks do this actually, because it turns out that they exert tension forces between fluid elements. And it causes this instability arises and it gives rise to turbulence. And that turbulence does exactly what I was describing that friction forces doing. It torques down the inner regions so they spread inward, it torques up the outer regions so they spread outward, and you're exchanging angular momentum and allowing accretion to proceed, releasing gravitational binding energy. That turbulence itself is dissipative, so all that gravitational binding energy that you're releasing goes into heat and goes into radiation and creates the fireworks that we observe. And in fact, the simulations of this is now an extremely old simulation, but from the 90s. This is a somewhat more modern simulation from the early 2000s. What you're seeing here are the electromagnetic energy fluxes from a black hole, and these are the jets that black holes form. And again, this is due to the magnetic fields that exist in this accretion flow. You're not seeing the accretion flow here, but that is how we think jets form. They actually do look like they're emerging directly from the black hole, although nothing can escape from the black hole itself. That's all old hat, though. So at UCSB, where this is being led by a postdoc who's at the Kavli Institute for Theoretical Physics, he's doing now simulations of these black hole accretion flows, but computers have now become powerful enough that you're not just including the magnetic fields to simulate the turbulent dynamics, you can actually put in the dissipation by the turbulence, allow the material to radiate photons, and you can put the photons in the simulation as well, and so you have everything. And you're actually looking at how the accretion flow would look to an observer, because you actually have the photons in the simulation. So, and these are revealing structures that we just didn't anticipate before these simulations existed, although we can understand them in retrospect. And here's some other simulations that we're doing. But what I want to focus on is, because turbulence is so central to how all of these things work, I want to study a type of system which is not as exciting as these black holes or protoplanetary disks where planets form and maybe intelligent civilizations. I am focusing these days mostly on white dwarf systems. So a white dwarf, like a black hole or a neutron star, which has a companion star, can rip material off of that star, and that material forms an accretion disk and produces fireworks, not as spectacularly as a black hole would, but fireworks nonetheless. So let me show you what I mean here. So Cygnus was already mentioned in the movie in the planetarium in connection with Cygnus X1. So there's the constellation Cygnus. I'm going to another place in that constellation, way over here, and there is a star or a system which is basically a white dwarf binary with an accretion disk, and this thing can reach magnitudes, apparent magnitudes in the optical, up to 8th magnitude. Okay, so it can get almost bright enough to see, but not quite. We can only see down to 5th magnitude. But almost that bright, and the system is called SS Cygni. So there it reaches 8th magnitude. This is its apparent magnitude is a function of time and days, in Julian days, and it goes up and down, up and down, up and down every few months, basically. It undergoes these outbursts. This is an accreting white dwarf that's doing this. It's not due to nuclear explosions on the white dwarf. It's not a nova. It's called a dwarf nova because it doesn't vary by that much. And in fact, we've been observing, humanity, actually you all, amateur astronomers, have been observing this for over a century now. So this is a light curve of SS Cygni, which starts way back in 1900, and this is going up to 2000. I guess I downloaded this from the BSO in 2010 or something. That is a continuous light curve that people have been monitoring for over a century. And yeah, the thing that I find most wow about this is that right through the world wars, both of them, the Depression, everything, somebody went out into their backyard and measured the apparent magnitude of this system continuously. And it wasn't just somebody, it was a whole series of somebodies that did this, and so it's been carried on as a tradition. And not only that, you know that detector technology has changed over this time scale as well, and yet the light curves up here look pretty much the same as the light curves down here. So they were doing it accurately over that time scale as well. It's just an amazing testament to humanity's interest in understanding the universe around them, right? And I just think it's wonderful. But from my perspective, the other thing that's wonderful about this is an incredible data set to play with. Because if you understand what's producing these outbursts, you can test your theories against these sorts of data sets. And it's not just this. I'll show you some even more spectacular data sets later on. This instability in the accretion disk, which I haven't described to you yet, what's causing it, that produces these outbursts, also exists in black hole and neutron star systems, and it explains why most black holes we actually don't know about in our galaxy. We have to wait until this instability happens in the disk, and suddenly a new black hole source appears on the sky. And we train all of our telescopes on it and monitor it, and then it just fades away, and sometimes it comes back, sometimes it doesn't. And so there are many black hole and neutron star systems which we don't even know about in our galaxy because they haven't yet outburst due to this instability. What this instability is that's causing this is, it's due to the fact that you're feeding this disk at such a rate that its temperature is just on the hairy edge of ripping electrons off of protons and hydrogen atoms to form an ionized plasma. It's at around 10,000 Kelvin or so. You're feeding it at just that rate where the plasma just doesn't know whether it wants to be neutral atoms, or ionized protons and electrons. And when you do that, it turns out the interaction between photons and matter is gigantic. The opacities of material go through orders of magnitude changes in that transition, in that thermodynamic transition. And that means that the disk itself, in terms of balancing the dissipation by turbulence, the heating, with cooling, has to sort of, whoa, if I ionize, I trap that heat, and then I can't cool so well, or if I go neutral, then I release that heat, and it tries to find this difficult balance between those processes, and it can't quite do it if you're locked right on that temperature. So it turns out that those temperatures that you're feeding it, it can't exist, actually. It has to go fully ionized, when it's then hot, and it can radiate, or it has to go fully neutral, and where again the opacity drops and it can radiate. It cannot exist between here, but you're feeding it, wanting it to be there. And so what that means, when you're feeding it there, it has no choice to go into this bright outburst state, but then it's processing material faster than you're feeding it, And so eventually it has to drop down in temperature because it's not getting enough gravity power to maintain itself at that high temperature. So you drop down, and then you're feeding it too fast, and so it can't stay cool, it has to heat up because it wants to stay that temperature, but it can't. So it just hops back and forth regularly, again and again and again and again. Yes?
And the masses of these stars, the white dwarf is more massive than a donor star always. And
Is it always?
the donor star is always going around the white dwarf.
Well, they're both going around their common center of mass.
Oh, common
basically.
center.
Yeah. So actually the systems that I'm most interested in, and I'll get to those later too, the donor star is substantially less massive than the white dwarf. So in fact, it's mostly going around the white dwarf. But I will show you a cool movie which you'll see. It's not quite. I mean, there's still a center mass, and they're orbiting around the common center mass.
So is there kind of a relationship between these novas and the masses of each?
Oh yes, yes, yeah. Actually, it's more connected to the orbital period of the donor star. So it depends. In other words, it depends. It is related to the masses, but it's more related to how far that companion star is. So in terms of the orbital period is determined by both, and that determines how much mass is coming into the stream, and that determines the feeding rate, and that determines whether you're at this unstable temperature or not. If the system is very, very compact, you're ripping material off of the companion star more quickly, which should make sense, the gravity is stronger. And then you're able to maintain yourself up here continuously. These are called nova-like variables because they look like outbursting dwarf novae, except that they stay in outburst forever and ever and ever. So they're not really varying, they're just dwarf nova-like variables, even though they're not variables. And but so you can stay up here, you can stay down here, but if you're being fed at this critical rate, then you have to hop back and forth. Okay. Is this making any sense? Please do interrupt me. Okay. So one of the mysteries of these systems is if you wanted to fit that 100-year-old light curve of SS Cygni, get any of the timescales right, you could do it with basic ideas about how this turbulence behaves, but there was a strange fact that in outburst, you had to have the turbulence being stronger than in quiescence. That had to be the case. If you don't have that, you cannot explain the light curves. And many people have tried and failed. And the only way to do that is when you're in outburst, when you're in this ionized state, you have to be really, really strongly turbulent. And in quiescence, it has to be weak. And nobody understood that until I claim, until we came along. I'm hoping this turns out to be the answer. So we have this suggestion as to what might be the answer. It turns out that opacity physics, right when you're triggering the ionization, when you're trapping that photons, when the opacity goes way, way up, you trigger convection. Rather than a simple disk, you get a pot that's boiling, and that turns out to affect the turbulence and enhance the stresses. And it turns out that the stresses that we measure in these simulations are exactly the stresses that were inferred by observations. This is a post-diction rather than a prediction, but we think we can, computers are now powerful enough that when you put in the thermodynamics and the dynamics of this magnetic turbulence, you can explain the stresses that were inferred by observations for a long time. So this has gotten people in the field very excited, and I'm excited about it. I hope it holds up. And now I'm going to show you, okay, so that's one result that we've been working on, but there's more that I find interesting about these systems. So this is another great spacecraft. The Kepler spacecraft, it's also now defunct, unfortunately. Its greatest claim to fame was that it detected exoplanets in spades. It detected more exoplanets than any other experiment that's happened, although there's a new satellite test that's in orbit right now, that's up there right now that will do interesting things. But it didn't just do exoplanets. So this is, what it did is it had exquisite photometry, and it was just monitoring a portion of the sky, at least the original mission, and it was just staring at everything in that field forever and ever and ever, measuring brightnesses on every minute basically. And it did this for years, okay? So this is a light curve of a white dwarf binary that happened to be in the Kepler field. And it undergoes outbursts, okay? And because you have this continuous monitoring for years, you got this very exquisite light curve. And the photometry is incredibly accurate. You see all these wiggles here? That is not noise. That is real variation in the slide curve. And in fact, there's this little blue box which is blown up here. That is not noise. That's a periodicity that you're seeing in quiescence in the system. It undergoes outbursts, outbursts, outbursts. This is interesting. This is called a super outburst. SS Cygni doesn't show these. These only arise in very compact systems. And again, you have these enormous periodicities here. And there's even down here, well, that's not noise, it's not as nicely periodic, but there are periodic variations down here too. So there's all this stuff that we want to try and understand. And these periodicities, by the way, are called super humps. And I wanted to get a volunteer to try and explain to you what these super humps might be. I was hoping that there would be a child, that would be best. But I'll take anyone.
Adrian Lopez. Adrian. Yo, Adrian.
Thank you, Adrian. Okay, so this is a very simple thing. In fact, sorry, let me just go to the, let's put that in context. So what I want you all to imagine, I'm going to be the companion star, and Adrian here is going to be the white dwarf and the accretion disk, okay? And so the accretion disk is not going to be completely circularly symmetric. It's going to be a little distorted, so I want you to stick your arm out there. Okay, great, and just hold it up. And I'm just the donor star, and yeah, there's not a lot of room here, and I'm just orbiting around Adrian here as best I can. Round and round and round. And if he's just staying there, so the disk has an asymmetry, but it's just fixed in orientation in space, then the system will reproduce itself every time I orbit round at the orbital period, right? And then I recover where I was, and the system will recover to its state. But if the disk is eccentric, that is, it's not completely circular, but it's a little elliptical, so that is represented by your arm out there. Adrian, because of the tidal gravitational field of me that I'm exerting on this disk, I'm exerting torques on that disk, Adrian will actually precess slowly, that's right. And so I will be going around, and I won't recover until I orbit a little bit more than an orbital period. Boom, I recovered now. And so you'll get a variation that's a little bit longer than the orbital period. That's called a positive superhump. Then there's another type of variation as well, and now I guess I want you to stick your arm like this or up, okay? So suppose the disk isn't eccentric, just eccentric, well, maybe it's eccentric too, but it's tilted, okay, out of the orbital plane of the binary. Tidal torques on that tilted disk will actually cause, it's the same thing the sun does on the inclined orbit of the moon. It actually causes retrograde precession, so you now go around this way, in the opposite direction, and now I don't have to orbit as far, boom, to recover my original position. So that causes a negative superhump, a periodicity that's a little bit less than the orbital period. Thank you. So does that? Okay, so these periodicities that exist in these systems are due to interesting dynamical interactions that the companion star is exerting on the disk, if it's eccentric or if it's tilted. So if it's eccentric, you should prograde precess and get a positive superhump. If it's tilted, you should get negative retrograde precession, and you should get a negative superhump. The trouble is, the system that we're now trying to simulate. Ooh, don't spoil it. So this is the system that I'm obsessed with right now. It's a nova-like variable, so it doesn't undergo outbursts because it's so compact. Everything's to scale here. That dot here is actually the white dwarf radius measured to scale. So that's the whole white dwarf. That's the whole companion star. It's about 0.1 solar masses. The white dwarf is around 0.8 solar masses, I think, in this system. And this system is going around its common center of mass once every, have a guess, what its orbital period is. What would you guess?
15 minutes.
Ooh! What did you say?
18 minutes.
Oh, yeah. 18 minutes. And you said 23. Okay. But okay, you were genuinely guessing. You weren't reading the slide. I applaud you, sir. Imagine that. Two stars with masses about the mass of the sun orbiting each other every 18 minutes. These are extremely close together, which is why the white dwarf, which is basically an object the size of the Earth, is that close to that companion star, so it's not much bigger than the Earth. And the entire distance between the feeding radius here and the white dwarf, that ratio is only a factor of 20. That is something that I can simulate on a modern supercomputer, the whole damned thing. Feeding it from the companion star, resolving the white dwarf, simulate the whole disk. All the tidal forces from that companion star. Let's actually look at this disk responding to these tidal forces. And put in photons, put in magnetohydrodynamic turbulence, put in the whole 9 yards, and let's see what happens.
So is the, pardon me,
Yes, go ahead.
is the star in the disk, embedded in the disk, the feeding star?
No, right. So what is this other stuff that I've drawn? This pretty stuff. Okay, so I use this as an example in a classical mechanics class at UCSB because I was also trying to demonstrate the physics of what are called Lagrange points. So did I just hear groans? So this is the inner Lagrange point where the force here from M2 is exactly the same thing as, but equal and opposite to the force on M1. So that's an equilibrium point, and these are also other equilibrium points. We use these in the solar system as places to put things like, where we will put JWST if it ever flies, and things like that. Right. So but this point, for this system, what we really care about is that inner Lagrange point. That's where the material is being ripped off the companion star. Okay. This system. So it was also observed by Kepler. This 18-minute orbital period for years. Okay. So we also have an exquisite light curve. Because it doesn't undergo outbursts, it's not as pretty as the one that I showed you, okay? So we've been observing the system, it's basically quiescent steady state for years, but it shows these periodicities, in fact, lots of periodicities, and including negative and positive superhumps. So, Adrian here, I won't ask you to come up again, but I would challenge you, okay, so he's got to do this and this, okay, tilted, and then he's got to precess, prograde, and retrograde at the same time. Because we see both periodicities. So he's got to be turning in two directions at the same time, which is a neat trick, if that's the correct explanation for what these periodicities are due to. And so I'm going to show you a simulation, which I should warn you, I'll be upfront, because again, I don't want to lie like I did last time. This simulation has a major numerical problem, which I will describe later, so you shouldn't trust it, but it's given us the solution accidentally, even though it's wrong, as to what might be going on. And it's a very pretty movie, so I'll show it anyway. Okay, so, oops, not that. Okay, so you can't see the companion star or the white dwarf because they're not, actually, they're really boundary conditions of the simulation. So you see the stream. You can see the white dwarf wobbling because both stars are orbiting their common center of mass. Anyway, we're feeding this disk, feeding it. The colors, by the way, represent how bright it is. So that's the photon flux because we have photons in this simulation. And you'll notice that some interesting things are happening. In particular, what I formed a disk, and basically near where this region where the stream is impacting the disk, the outer material that's spread out from there is tilted up. And so, of course, what I needed is Adrian and one of his companions up here, and they're both, I need to split the disk into two. I need to have an inner eccentric disk, which is processing prograde, and an outer tilted disk, which is processing retrograde at the same time. I need to have two disks there in order to get this to happen and see this periodicity. This was extremely exciting when we first generated it. And again, this is an observed system, so we can compare it directly to observations, do all of that, even plot light curves because we have photons in the simulation, all of that great stuff. Except it's wrong. And this is what my graduate student in the last 6 months proved conclusively. Because we wanted to understand, okay, what's causing this tilted disk? And so we investigated how angular momentum was being conserved and what the torques on the system were. And it turns out that it's all numerical garbage associated with an unresolved, too few grid cells at the point of impact, and that introduces artificial torques, which ends up tilting the outer disk. So it is complete garbage. But I'm convinced that this is nevertheless the answer. It's just that I need to figure out a way of creating this configuration physically. And there is a way. This happened very early on in the simulation, but it turns out that there's an orbital resonance with the companion star, which is way out here. And if this disk spreads out that far, theoretically, you should be able to excite both eccentricities and tilts. And I'd be willing to bet that the thing splits when it hits that resonance. And so we're running simulations at much higher resolution right now to try and get there. So we'll see what happens. Maybe I'll have a different story to tell you. So to summarize, I hope I haven't gone on for too long or too short. So these rotating disks are ubiquitous. I've been studying them all my life. I find them very fascinating, and I hope you found this moderately interesting. When they're orbiting black holes, they can release enormous, absolutely enormous amounts of power. And so that's something that I've been studying again all my life, and not all my life, all my adult life. It's complicated. The reason why this isn't easy is because it's turbulence. And so it requires an interaction between observational data, theoretical ideas, and modern supercomputer simulations, and trying to combine all of these things to get ideas as to what's going on in these systems.
Are you
And-
running into a small difference between big numbers problem that when you're trying to do this?
That's precisely the problem. Actually, I can explain the numerical problem. This is something that my graduate student figured out, and I thought, wow, yes, brilliant, yeah. I mean, I'm actually excited about the fact that it's wrong, because we were using a very popular code to do this, and it turns out we've revealed a vulnerability in this code, which you can improve on with high resolution, and we were just running it at low. So it turns out this code is very good at I'm going to get technical for a second. It's very good at conserving linear momentum. It's designed to conserve linear momentum to machine accuracy. But if I have a grid cell and I have a shear flow, which I have all over the place here, and I advect these momenta into the same cell, they annihilate, okay? As they should, that's fine. But they also have angular momentum there. That gets annihilated, and boom, you've lost angular momentum. So it turns out that this code can't do both conservation laws at the same time.
What code do you
And that's
use?
Athena++, if you've heard of it. It's a code that comes out of Princeton, and it's widely used. It's a superb code, but I think any grid code is going to have this problem, actually. I don't know how to solve it, but fortunately, as you increase resolution, it becomes less of a problem. But it makes the simulation more expensive, too. Yes?
When the Walt Disney motion picture came out, The Black Hole, about 30 years ago, was it a flop because they didn't know as much as you know now?
No. No, it was a flop exactly because it was a bad movie. Yeah, no, yes, and don't talk to me about Interstellar either. I do believe in love, I do believe in gravity, but I don't think gravity is love. Yes?
So the word magnetohydro, hydro always sounds like water to me.
Yes,
But
it's a fluid.
fluid, okay, so
yeah.
hydro actually means fluid, okay,
Yeah.
not just water.
Yeah.
And then there's thermodynamics,
Yes.
which is this
Heat flow. Yeah, so heating and cooling. And that's that. So in heating, and in particular heating and, well, cooling by photons, the way we see everything electromagnetically anyway, before the advent of gravitational waves, and neutrinos, by the way, we see the sun radiating energy in photons, and so the sun is cooling, or would be cooling if it wasn't for nuclear reactions that provide heat at the core. Actually, it wouldn't cool, it would heat up, because it would contract under gravity and get hotter. But yeah, that thermodynamics matters here.
And plus gravity.
Yeah. Yes, it's a complicated simulation. Yes, that's why it requires modern supercomputers. So the simulation that I just showed you ran, it took a couple of months to run on NASA's most powerful computers, which, by the way, I can't report the most recent progress on this because those supercomputers are down, because the government shut down, so we cannot run any simulations right now at the moment. Not that I'm frustrated at all. I'm sorry?
Are you getting paid?
I am getting paid, yes, because I'm not paid by the federal government, I'm paid by the state of California, yeah, so the University of California, yes. Oh, it's big, so it's again, technical, it's not a uniform mesh, so we put in most of ours, it's a static refined mesh where most of the zones are in the orbital plane, of course, and close to the white dwarf. but it has an equivalent, at the highest resolution, it has an equivalent resolution of 512 cubed, which is, you know, with this sort of code is about as good as you can do nowadays with that amount of physics in it. And using CPUs. There are other groups who are now transitioning to GPUs who are claiming that they can get much, much higher resolution. And so this is something else that we're going to have to consider. Sorry, somebody else? Yes?
If I can get back to just basics for a second here.
Yeah.
Would it be fair to say that in nature, there's always a tendency for any mass of matter to become a pancake? Or it's gonna collapse in on itself. It's got to orbit on what we call the ecliptic now, which is the remains of the solar system.
Yeah.
And yet, out there in all those pancakes that are spiral galaxies, there are cotton balls.
Yes.
Whatever those things are called, I forget.
Bulges.
How do they, is that a totally different dynamic and totally different physics?
Yes and no. So it's basically about the role. So something has to support you against gravity to give you a finite size. Otherwise, you collapse into a black hole.
Exactly.
The sun is a sphere. The Earth is a sphere. Actually, let's not talk about the Earth because the Earth's not a fluid. But the sun is basically supported against gravity by random motions of the particles, the ions and electrons that make it up. It's a galactic bulge, this sort of cotton ball as you described it, is also supported, in a sense, if you look at the bulge as a whole, by random motions of stars. Not a lot of rotation, although some of them are rotating a little bit, but it's supported mostly by the random motions. A disk, like a spiral galaxy, or way out here in the Milky Way, in the disk component of the Milky Way, that's really supported by rotation. So, the difference really is when did the stars form out of the gas that was collapsing? So, any gas that's collapsing will generally have some sense of rotation to it, and again, as it's collapsing under its own gravity, it's going to pull its arms in and rotate faster and faster. And eventually it will become rotationally supported. This is probably not what happened with galactic bulges, but one way of imagining it is as it's on its way to collapsing, you start forming stars before you become rotationally supported, and then you form a cotton ball. But if you do become rotationally supported and form a disk, and then form stars, you're going to end up with a stellar disk. The other complication, though, is the galaxies collide with each other, and even if you take two spiral galaxies and smash them into each other, you end up with a big cotton ball. So giant elliptical galaxies all came from that formation.
Well, our Oort cloud is a shell. It's not part of
Yeah.
accretion.
So the Oort cloud.
We get it later.
Yeah, I think the reason why the Oort cloud is roughly spherical is because of the action. It was originally a disk, but then passing stars and, believe it or not, the tidal field of the entire galaxy, it's way out, far away from the sun, and there are the gravitational field of the galaxy starts to perturb the orbits out of the orbital plane of the sun, and that you can show. So I worked on that when I thought gamma ray bursts were, never mind. It was a crazy idea, which was absolutely wrong. And that's the entire extent of my knowledge about the Oort cloud. But I do know that the galactic gravitational field affects orbits when you go way out there.
Is this the same physics that gives us hurricanes and twisters, you suppose? Something wants to go around and around rather than collapsing? That's heat and air, and heat versus cold and its other forces, but I'm wondering if it's the same.
It is related. Maybe a more direct example is a kitchen sink vortex, what we call. So the material is running down the drain, but there's a little bit of sense of rotation, and it starts to rotate faster and faster and forms this vortex. Yeah.
Well,
Ready to? Oh, yeah.
In the movie, it said, what was the sun finally?
You're not quoting the black hole. The
No.
Disney black
I should have, it's not. But, they said the sun was gonna burn out in like 5 million years.
Billion.
5 billion years.
Yeah.
At that point, what?
Yeah, phew, it's not a million years.
What would it be like on the Earth at that time? I mean, is this gonna be like global warming, global cooling, global warming?
Oh, no, when the sun will, the first thing that will happen is that the core will contract because it's no longer supported by hydrogen fusion, and as it contracts and it gets very, very dense, and then hydrogen fusion starts happening in just on the surface around that contracting core, and it fuses actually much more rapidly. It releases much more energy than the existing sun. So what happens is the whole sun swells up and becomes much more brighter. And so and it will swell up to about the orbit of the Earth. And so we will have the sun right in our faces, enormously bright, and we will fry. Yeah, it's global warming on.
But 5 billion years off, not 5 million.
Yes.
So you can rest assured.
Yes, yeah.
What a hero state.
Well, thank you very much for your attention.
You did good, Professor. We
Okay.
appreciate it. We'd like you to take our official astronomical unit
Oh, awesome.
and a little piece of paper in this priceless porcelain mug, which is ours. Ask you one thing, if you would start the line at some point and then ask you just questions that you have as he's eating. So, let's eat, and you can leave those here if you want.
Okay, thank you. Thank you so much. By the way, thank you for all the work you do on the community. That was very impressive. Very
You can leave it down. Right there. That's good. It's on the front desk. Yeah.
Right now.